Okay, here we have a mass of 15 kilograms, and it has several forces acting on it. There's an applied force to the right of 22 newtons. We know this to be a positive 22 newtons because the vector is going to the positive x-axis direction. We also have static friction and kinetic friction. Now, you never add static and kinetic friction together. What these are, it's telling you if this object is not moving. If it's stationary, it's going to have a static friction of 23 newtons. If it is moving, it's going to have a kinetic friction of 12 newtons. So in order to get this thing started, if it is at rest, if you do have static friction, basically it's saying it needs at least 23 newtons in the other direction to create a net force of 0, and therefore you could have a constant velocity if you could apply at least 23 newtons. But once you get it going, you no longer have static friction, because static friction is when your mass is not moving. So then you would have kinetic friction. So if the object is already in motion, you only need 12 newtons to keep it going. So here, and also we have an 8 Newton force being applied downward to this object. It's very, very, very important to always keep your x and y axis variables separate. So always keep x and y separate. It's one thing you need to remember before we begin this problem. Alright, so it says, will the object at the left start moving? Well, to get it to start moving, we're assuming that it's stationary. It's currently not moving. If it's not moving, we're going to have a static friction of 23 newtons. Well, the applied force, someone's either pushing or pulling on this object to the right, it's only 22 newtons. 23 newtons, the friction is greater than the force we can apply. So will the object at the left start moving? The answer is no. Why or why not? Well, your static friction is greater than the applied force, your 22 newtons. If it is already moving, calculate the acceleration of the object. So if it's already moving, we only need 12 newtons to keep it moving. Well, we actually have 22 newtons. So to find the acceleration of this object, we actually have to find the net force. To find the net force, we already know that we have a force to the right being applied, this 22 newtons, and then we have the force of friction opposing that motion. Since it's moving, we're going to have kinetic friction, so it's actually negative 12, since it's going to the left, newtons. Alright? So 12 newtons pulling it to the left, and then we have a positive 22 newtons pulling it to the right. So our net force, the sum of our forces, is going to be negative 12 plus 22. Let's grab our calculator. Negative 12 plus 22. And some of you might have guessed it's going to be a net force of 10. So that's positive 10 newtons. Okay. So it's going to be moving 10 newtons with a force of 10 newtons to the right. But we don't want necessarily the force, we want the acceleration. We know that force equals mass times acceleration. So 10 equals 15, which is our mass, 15 kilograms, times our acceleration. So in order to solve for our acceleration, we have to divide both sides by 15. Well, 15 over 15 is just 1, so these cancel out, and you get 10 over 15. So our acceleration equals 10 over 15, which is 0.67. This is meters per second squared. Now it says, what is the weight of the object? Well, so far we've been dealing with the x-axis for A, B, and C, but now we are talking about something completely different. Talking about the y-axis. For these next two problems. So the force of weight, we actually have an equation for force of weight. The force of weight equals mass times gravity. So we know that our mass is 15 kilograms. Gravity is 9.8. When we multiply those together, we have a force of weight of 147. So it's 147 newtons, and technically it's going to be down because that's the force of weight. Now it wants to know, what is the normal force acting on the object? If the object were just sitting on this table and it had no other vertical or y-axis forces acting on it, then the normal force would be equal and opposite to the force of weight. But we have 8 additional newtons acting downward to this object. So what we have to do is we have to add 8 newtons to 147 newtons in order to get the normal force. And think of it this way. If you get on a scale and look at your weight, you're going to have a force of weight of however many pounds that is. But say you pick an object up. Say you pick up a bowling ball. The normal force, the force of weight that the scale is going to tell you is going to be more. You're applying an additional force downwards. Except, does your weight change? No. So the force of weight doesn't change, but the number we're going to see, the force that the ground has to apply back up to keep you on the surface, is going to be greater. So 147 plus 8 is 155. So the normal force is actually 155 newtons for this object. It says, use the equation for friction to find the coefficients of static and kinetic friction, mu s and mu k for the surface. So we know that there is a formula for kinetic and static friction. Kinetic friction is equal to mu k times the normal force, Fn. So if we were to rearrange that to solve for mu k, we could divide both sides by Fn. Well, Fn over Fn is 1, so we can cancel those out. So what we get is the kinetic friction coefficient, mu k, is equal to the kinetic frictional force, over the normal force. We know that the kinetic frictional force is 12 newtons. So here we're going to put 12 newtons. And we just solved for our normal force. We know that our normal force is 155. So we plug that into the calculator, 12 over 155. And we get 0.08. So our kinetic friction is 0.08. So our mu k equals 0.08. And since the friction coefficient does not have units, we are done finding the kinetic friction coefficient. Now, just like mu k equals the kinetic frictional force over the normal force, our μs, the friction coefficient for static friction, is going to be the static force over the normal force. We know that our static frictional force is 23 newtons.
Did that get it for you?
Yeah, it does. Alright, we're going to get 23 newtons over our normal force, which we calculated to be 155 newtons. So we plug that into the calculator. 23 over 155. And we get 0.15. So our static friction coefficient is 0.15.